Hello, this is our presentation on our honors project for the Differential Equations class taught by Professor Hebda. Today we'll be taking a look at Lab 7.2, Lost in Space in our textbook. Members of this project include Sean Kim, Jaclyn Heigert, and Matt Draper.
This lab is called Lost in Space. In this lab, you are an astronaut in deep space on a mission, but your partner has left you drifting in space without any fuel in your suit to propel you. There is, however, an escape capsule 100 meters away from you. Both you and the capsule are stationary to begin, but you realize that the gravitational force between you will eventually pull you together. Your mass is 150 kilograms, and the capsule's mass is 10 to the 6th kilograms. Your job is to find out how long it will take for you to reach the capsule and how fast you will be approaching the capsule when 1 meter apart. In this lab, we began by converting the given second-order differential equation into a first-order system, and we used that first-order system to plug into the numerical techniques of Euler's and Runge-Kutta method. And we use these to find the time it will take and the velocity when you are a meter apart from the capsule. We then use these values that we found from the numerical methods to verify that the time calculation was accurate within 1 second. When thinking about motion in space, there are two laws that are very important to consider. The first law is Newton's law of motion, which tells us that force is equal to mass times acceleration. The second law is Newton's law of gravitation, which tells us that the distance between two objects and the gravitational force between the two objects is inversely proportional. The two objects in this lab are the escape capsule and you, the astronaut. These two laws give us second-order differential equations, which tell us position as a function of time. These two equations are considered to be the first differential equations, and they were very important in the time of Sir Isaac Newton because they gave an estimation for the position of the moon. And knowing the position of the moon was important for navigation of the sea back then. These equations are still used today for space navigation, and this lab gives an example of how they could be used. So in order to begin this lab, we first need a differential equation. And because both you and the capsule begin as stationary, there's only one force acting between you, and it's the force of gravity, meaning that you are moving in a single line, so we only need one number to denote the position. We can say that x1 is your position as the astronaut, and x2 is the position of the escape capsule. And we're assuming that x2 is greater than x1. We can then say that x is equal to x2 minus x1 to give us a single value for the distance between you and the capsule. Then, by applying Newton's laws of motion and gravitation, we can arrive at equation 1. And by manipulating this, dividing by 150, we get equation 2, and equation 3 tells us the acceleration of the astronaut. So by subtracting equation 3 and equation 2, we get equation 4, which is the equation we will be using in this lab. It's a nonlinear second-order differential equation. And in this equation, g is the gravitational constant, which is equal to 6.6732 times 10 to the negative 11th.
This differential equation is found by taking the acceleration of the capsule minus the acceleration of the astronaut, as x represents the difference in position between the capsule and astronaut. Here, x is measured in meters and starts at a difference of 100, approaching 0 as the astronaut and capsule meet. The other variables in this problem include t as time in seconds, and y as velocity, measured in meters per second. The constants seen in this equation are gravitation, or g, equivalent to 6.6732 times 10 to the negative 11, the mass of the astronaut at 150 kilograms, and the mass of the escape capsule at 10 to the 6 kilograms.
Problem 1 is the basic conversion of the second-order differential equation to a first-order system. So we begin with the equation which is given to us, that is, x double prime is equal to the negative gravitational constant times the quantity 10 to the 6th plus 150 divided by x squared. We can define x prime is equal to y, and therefore x double prime is equal to y prime. So using these definitions, we can say that the first order system is x prime is equal to y, and y prime is equal to negative gravitational constant times the quantity 10 to the 6th plus 150 divided by x squared. The initial conditions for this system are x of 0 equals 100, because at time 0 you are 100 meters away from the capsule, and y of 0 equals 0, because at time 0 neither you nor the capsule are moving. Doing this conversion to a first order system is important because this is what we will plug into both Euler's and Runge-Kutta method later on, and these are the equations we use to help find how long it will take for you to reach the capsule and the velocity that you are approaching it when you are 1 meter apart.
In the first part of problem 2, we were asked to approximate the time necessary for a person to reach the escape capsule, given that they started 100 meters away and both them and the capsule have initial velocity 0. In order to solve this problem, we used both numerical techniques and MATLAB computations to estimate the most accurate time. By determining at what step the distance between the capsule and person is 0, or when the value goes from positive to negative, we can solve for the time by multiplying by the specific step to the step size. In the second part of problem 2, we were asked to determine at what velocity is the person and the capsule coming together when they are 1 meter apart. Again, using numerical methods and MATLAB, we found the step at which the distance was 1 meter away and correlated that to the step for the corresponding y variable. As explained before, this y variable represents the velocity at each step. The first numerical method used was Euler's method. Euler's method uses the idea of local linearity or linear approximation, where we use small tangent lines over a short distance to approximate the solution to an initial value problem. In order to approximate our initial value problem, we inserted our second-order differential equation along with x of 1 equals 100 as in starting 100 meters apart, and y of 1 equals 0 as in the initial velocity of 0. Our step size started at 100, and we continuously decreased this value until we received a more accurate time. The step size determines the accuracy within each subinterval, and the number of steps allows several calculations to be found for each of these steps. Shown on this slide is a table of our Euler's method approximation. It's important to note that as we decrease step size, we must correspondingly increase the number of steps. If the step size is cut in half, the number of steps must be doubled. The next column, x equals 0, shows us the specific step at which the distance between the capsule and person is 0. In order to find the time, we multiply the step by the step size. The time approximation is given in both seconds and hours. However, note that the error exists in our time in seconds, as x equals 0 was given to us as a range between two steps. The last two columns give us the step at which distance between is 1 and the corresponding velocity for that step. Euler's method showed a slow increase in accuracy of time as step size decreased. The approximation of 1 second brought us down to a step size of 0.5 and time in seconds as 135,994. Our velocity was 0.0115 when 1 meter apart. The second numerical method we used was Runge-Kutta's method. Unlike the Euler's method, which calculates one slope at a time, the Runge-Kutta calculates 4 different slopes and uses them as weighted averages. The Runge-Kutta method is more accurate than Euler's method at the same step size and only requires a little more computation at each step. In both methods, decreasing the step size and increasing the number of steps improves the accuracy of the approximation. The error in Euler's method is roughly proportional to the step size h, while that in Runge-Kutta is proportional to h to the 4th power. In order to approximate our initial value problem, we inserted the same second-order differential equations and initial conditions as Euler's method. Shown on this slide is a table of our Runge-Kutta method approximation. We started it at the same step size as Euler's method and continued to decrease till our approximation was accurate within 1 second. The same calculations as explained before were undertaken for each respective column. The largest noticeable difference is that Runge-Kutta method showed a much faster increase as step size decreased. The final approximation to 1 second brought us down to a step size of 1 as opposed to 0.5 in Euler's, and time in seconds as 135,992. This equivalates to 37.776 hours. Our velocity when 1 meter apart was 0.0114 meters per second.
Problem 3 asked us to verify the time taken to reach the escape capsule with an accuracy of 1 second. Based off the results of Euler's method and Runge-Kutta's method approximations, it can be first noted that the accuracy improves as the value of the step size decreases. As the step size becomes smaller, as does the change in time, or delta t. This means the time approximation is becoming increasingly accurate. Since a delta t of 1 can be seen in each table, it can be said that both methods return times with accuracies of 1 second. However, Runge-Kutta will be used to collect the final results of the lab, as returning a 1 second accuracy in fewer step sizes shows a higher accuracy. Because of this, the final time approximation, accurate to within 1 second, is 135,992 seconds, or approximately 37.78 days. To conclude the lab, Problem 1 first asked to convert the second-order differential equation given into a first-order system of equations, which was found to be x prime equals y with an initial condition of x of 0 equals 100, and y prime equals negative g times 10 to the 6th plus 150 over x squared, with an initial condition of y of 0 equals 0. Problem 2 asked 2 parts, with the first being how long it takes for the astronaut and capsule to meet, which was found to be 135,992 seconds, or approximately 37.78 days. The second part of this problem asked how fast they are approaching each other at 1 meter apart, which was found to be a velocity of 0.0114 meters per second. Both of these parts were found using both Euler's method and Runge-Kutta's method of approximation. However, Runge-Kutta was used for the final results because of a higher accuracy, which was determined because fewer step sizes were needed when solving Problem 2. Problem 3 asks to verify the time computation to within 1 second. This accuracy can be seen from the table, where a step size from 3 to 1 gives a delta t of 1, so 1 second accuracy at 135,992 seconds.